Hello Calculus, we are going to do the example question, what I call the big FRQ, for area volume. So let's read. It says, let R be the region in the first quadrant enclosed by the graph of f of x above. So here's y equals f of x, and g of x below. So this is y equals g of x. As shown in the figure, the graphs intersect at the origin here and at the point A, comma, B, okay? And this is for our big FRQ, this is basically just like setup only, okay? So just as a reminder, if we go top minus bottom, we're going to be in terms of x. If we go right minus left, we're going to be in terms of y. Okay, so for part A, if I want to find the area, there are two ways. We can go integral and use our domain, so our x's. So from x equals 0 to x equals a, of top minus bottom, so that would be f of x minus g of x dx. Or we could go integral using our y values, so from y equals 0 to y equals b of right minus left, so that would be g of y minus f of y dy. All right, part B, it says find the volume when R is rotated about the horizontal line y equals 1. So I'm first going to draw that line here. Notice that we do have empty space, right, between that axis of revolution and that region R. So we're going to start at our axis and go to our farther function. That is going to be capital R for radius, not to be confused with the capital R for region. And then go back to your axis of revolution, go to your closer function, and that will be little r. All right, so in this case, we're going to go pi integral from x equals 0 to x equals a of capital R, which is top minus bottom, so that is 1 minus g of x squared minus little r squared. Again, top minus bottom, so 1 minus f of x, quantity squared, and then that whole thing dx. Part C, find the volume when region R is rotated about the vertical line x equals 1. So let's draw that vertical line here first. At x equals 1, I'm going to say right here, let's assume that A is 1. All right, so as we are rotating here, we are going to go right minus left, so always start at your axis of revolution and go to your farther function, that's capital R, back to your axis of revolution, go to your closer function, that's little r. So I've got, this will be in terms of y, so pi integral from y equals 0 to y equals b, and then going right minus left, you've got 1 minus, and that will be f of y, squared minus, and then we need to take little r and square it, so 1 minus g of y, squared, and that whole thing, dy. Part D, region R is the base of a solid. For this solid, find the volume if each cross-section perpendicular to the x-axis has an area A of x. Okay, so anytime you want to find volume, given the cross-section, you're just going to integrate. So you always integrate area to get volume. In this case, I can tell I'm in terms of x since we're perpendicular to the x-axis, so I'm going from x equals 0 to x equals a, and then whatever formula they give you for a of x, that is what you will integrate or anti-derive if you have no calculator. All right, and that is it. Now, in most cases, they are not going to give you the area formula. You will need to figure out the area formula on your own. So, for part E, it says that we want to find the volume if cross-sections perpendicular to the x-axis again. So I can tell that we are, so you can go top minus bottom. And then they give me what shape we're using, okay? So if I want to use squares, with a side in R, that would top minus bottom slice I just drew there, that would represent one of my sides. So we're going to have an infinite number of squares, which is side squared. So again, use your x values, and then your side in this case is top minus bottom. And notice you've got three dimensions there, right? You've got the square, and then the dx is a dimension as well. All right, so I am going to go ahead and force a pause on the screen, see what you remember for the other area formulas. All right, so here's what we have for the next three, and the coefficients are the really important pieces to remember, right? So pi over 8 for semicircles, 1/2 for isosceles right triangles, and square root of 3 over 4 for equilateral triangles. Okay, so what if we have rectangles? Well, a rectangle is base times height, right? So I'm taking infinite sum from x equals 0 to x equals a. Your base is top minus bottom. That's the part that is in the region R. So base is that times height, h of x, and then that tiny, tiny thickness dx, okay? Another scenario you might have, rectangle still, base is still in R, but height is twice the base, right? So height is twice the base. So then you want to make a substitution for area, because area is base times height, right? I can substitute in 2b for h, which gives me base times 2 base, which is equal to 2 base squared. So we can come into our integral now and go integral from x equals 0 to x equals a of 2. I'm important to bring that out of the integral. And then base, which is f of x minus g of x squared. Okay, and that's probably the more common way, where they'll tell you, you need to figure out essentially the height in terms of the base, because you need to get your integrand in terms of the base, since that's the part that is in region R. Now, in this case, all of my example, all our shapes are perpendicular to the x-axis. If our cross-sections were instead perpendicular to the y-axis, very similar, it's just that you'd be in terms of y, and you'd be going right minus left instead of top minus bottom. Part F, the horizontal line y equals k divides region R into two regions of equal area. Write the integral of that equation that would give the value for k. All right, so let's eyeball y equals k. Let's see if we can kind of divide the area into two equal regions. And I want the area below that line to equal the area above that line, right? And in this case, notice that you're going to need to fill in going this way, going right minus left, okay? So for area, that bottom piece that I just filled in, that'll be the area from from y equals 0 to y equals k of right minus left dy, and I want that to equal, you got to have an equal there, no arrows, the area above that. And so that area, that's the infinite sum from y equals k to y equals b, and still right minus left dy. All right, part G, the vertical line, x equals k, divides the region R into two regions of equal area. Write an integral equation that would give the value for k. So again, let's eyeball the line y equals k that divides, x equals k that divides that region into two equal areas. Again, I want the region to the left of that line to equal the region to the right of that line. And in this case, I will fill in going top minus bottom, so that would be in terms of what? In terms of x. So we are going to go the integral from x equals 0 to x equals k of top minus bottom dx. Remember, that's how we find our area. I need that region to equal the region from x equals k to x equals a, of top minus bottom dx. All right, part H, region R models the surface of a pond. Find the volume of the pond if the depth of the water in the pond is given by dx. So this is actually very similar to putting rectangles in their region with a height of h. It's just now we're calling it depth instead of height, essentially. So you can tell we're in terms of x, so I'm going to go integral from x equals 0 to x equals a, and we're going to find that area, which will be top minus bottom. And remember, volume is essentially area of the base times the height. So we've got this times dx times, those are bad letters, d of x, and then dx. All right, d of x is the depth, dx is your usual differential. All right, that is it.